Newton's second law of motion. Isaac Newton, the father of classical mechanics, gave us two fundamental equations, F equals ma, where F represents the net force acting on an object measured in newtons, and m represents the mass of the object measured in kilograms, kg. A represents the acceleration of the object measured in meters per second squared, m/s squared. Force equals mass times acceleration. It's a very powerful equation. In classical physics, force means a push or pull. Mass measures how much something resists moving, and acceleration is how quickly something speeds up. When you apply a force to an object, it determines how fast it will accelerate. Imagine pushing a shopping cart. The harder you push, force, the faster it moves, acceleration. The cart's mass determines how much force is needed. Force is not a physical thing you can hold, but a way to describe how objects affect each other. Your body has mass, which is the amount of matter in it, like how many Legos are in a building set. Your weight is the result of Earth's gravity pulling on your mass. It's like the pressure all those Legos put on the table. So technically you don't weigh 72 kilograms because that's your mass. Your weight is a force measured in newtons. You should say you weigh 706 newtons, which is your mass multiplied by 9.81 m/s squared, the gravity that pulls on Earth. Newton's law of universal gravitation. Imagine watching an apple fall from a tree straight down to the ground. This simple observation sparked Isaac Newton's curiosity and led to the development of his law of universal gravitation. The law of universal gravitation explains how objects attract each other due to gravity. This law helps us understand why objects attract each other due to gravity, like how the Earth's gravity keeps the moon circling around it and how gravity pulls an apple towards the ground instead of floating away. Think of gravity as a force that pulls any two objects with mass towards each other, similar to how magnets attract when they're close together. The strength of this pull depends on two things. 1. Force and mass are directly proportional. The more mass an object has, the stronger the pull. If one object is twice as heavy as another, its gravitational pull is twice as strong. 2. Force and distance are inversely proportional. The longer the distance, the weaker the force. Just like magnets that pull weaker as they move further apart, gravity also gets weaker the more distance there is between objects. If you double the distance between the two objects, the gravitational pull becomes 4 times weaker. Expressing this concept mathematically, we get F equals g m1 and m2 over r2, where F represents the gravitational force between two masses measured in newtons, and g is the gravitational constant, approximately 6.674 times 10 to the negative 11th power, and m squared, kg to the negative 2nd power. m1 and m2 are the masses of the two objects, measured in kilograms, kg. R is the distance between the centers of the two masses, measured in meters, m. Energy. Energy is a key concept in physics that came about a century after Newton's time. Unlike forces like pushing or pulling, which have both magnitude and direction, energy is just a number that tells us how much work can be done. It doesn't point anywhere like a force does. Work is a way of measuring how we transfer energy. When you apply a force to move something, like lifting an apple 1 meter up with the force of 1 newton, you do work. This work equals 1 joule of energy. In simple terms, work is how energy is used to move something. Whenever you store or use energy, you deal with potential or kinetic energy, two forms that can convert into each other. Both types of energy are measured in joules, named after the English mathematician James Prescott Joule. Kinetic energy. This is energy due to motion. Potential energy. This is energy stored in an object due to its position or state. Imagine you have a hammer in your hand. When you lift the hammer, it gains potential energy. As you let it fall to hit the table, that potential energy converts into kinetic energy. Here's a breakdown. First, the lifted hammer has more potential energy because it can move higher or lower. Second, as the hammer falls, its potential energy changes into kinetic energy. Third, when the hammer hits the table, it stops, and its energy becomes potential energy once again. Throughout this process, energy is neither lost nor destroyed, illustrating the law of conservation of energy. Potential energy is related to an object's position, while kinetic energy is related to its motion. They constantly convert into each other in a continuous cycle. Expressing these concepts mathematically, we get potential energy PE. This is the energy an object has because of its position. Think of a hammer held up high. It has the potential to fall due to gravity. The formula for potential energy is PE equals mgh, where m is the mass of the hammer, how heavy it is, g is the acceleration due to gravity, how fast it speeds up when it falls, about 9.8 m/s squared. H is the height above the ground. Kinetic energy, Ke. This is the energy an object has because of its motion. Where the hammer falls, it speeds up and gains kinetic energy. The formula for kinetic energy is Ke equals 1/2 mv squared, where m is the mass of the hammer and v is the velocity, how fast it's moving. Thermodynamics. Thermodynamics is the study of heat, energy, and how they interact. It's all about understanding how energy is transferred from one place to another and how it changes form. Let's look at a few examples to make things clearer. System and surroundings. In thermodynamics, we often talk about a system and its surroundings. The system is the part of the universe we're studying, and the surroundings are everything else. For example, if we're studying a hot cup of coffee, the coffee is the system and the air around it is the surrounding. Zeroth law of thermodynamics. This law states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. For example, if a thermometer, third system, reads the same temperature when in contact with two different objects, those two objects are at the same temperature. For example, imagine you have a cup of hot chocolate, system A, and a glass of cold water, system B. You also have a thermometer, system C, to measure their temperatures. When you place the thermometer in the hot chocolate, it shows a temperature reading. When you place the same thermometer in the cold water, it shows a different temperature reading. Now, if you place the thermometer in your room, system D, which is at room temperature, it will show a specific temperature reading. If you leave both the hot chocolate and the cold water in the room for a while, eventually the thermometer will show the same temperature for both liquids when you measure them again. This indicates that both the hot chocolate and the cold water have reached room temperature, thermal equilibrium with the room. According to Zeroth's law of thermodynamics, the hot chocolate is in thermal equilibrium with the room. The cold water is also in thermal equilibrium with the room. Therefore, the hot chocolate and the cold water are in thermal equilibrium with each other because they both have the same temperature as the room. First law of thermodynamics, the law of energy conservation. This law states that energy cannot be created or destroyed, only transferred or changed from one form to another. For example, imagine you're riding a bicycle up a hill. As you pedal, you're using chemical energy stored in your muscles from the food that you ate. This chemical energy is converted into mechanical energy as you push the pedals and move the bicycle forward. As you climb the hill, some of the mechanical energy is also converted into potential energy because you are gaining height. According to the first law of thermodynamics, the energy you used to pedal the bicycle did not disappear. Instead, it was transferred from one form to another, from chemical energy in your muscles to mechanical energy of pedaling, and then to potential energy as you gain height. The total amount of energy remains the same throughout the process, showing that energy is conserved. Second law of thermodynamics. This law states that energy tends to spread out and become more disordered over time. This is often described as the increase in entropy. For example, imagine you spray some perfume in one corner of a room. Initially, the perfume molecules are concentrated and confined to a small area, low entropy. As time passes, the perfume molecules start to spread out and mix with the air in the room. According to the second law of thermodynamics, the energy of the perfume molecules causes them to move and spread out from the area of high concentration to the rest of the room. This spreading out of the perfume molecules increases the disorder, the entropy, of the system. Eventually, the perfume scent will be evenly distributed throughout the room, illustrating how energy and matter naturally spread out and increase entropy over time. Third law of thermodynamics. This law states that as the temperature of a system approaches absolute zero, the entropy, or disorder, of the system approaches a minimum. Absolute zero is the lowest temperature possible, where particles have minimal motion. For example, imagine you have a jar of honey. At room temperature, the honey is a thick liquid with its molecules moving around but still somewhat orderly. As you place the jar of honey in the refrigerator, the temperature drops and the honey becomes thicker because the molecules move less and arrange themselves more orderly. According to the third law of thermodynamics, if you were to keep cooling the honey further and further, down to extremely low temperatures, the movement of the honey molecules would decrease even more, becoming very slow and highly ordered. As the temperature of the honey approaches absolute zero, which is theoretically the lowest possible temperature, the entropy, or disorder, of the honey would approach a minimum. The molecules would be in their most orderly and least energetic state. This illustrates that at absolute zero, the system's entropy is at its lowest because the particles have minimal motion and are in their most ordered state. Thermodynamics is all about energy transfer and transformation, and these principles are at work all around us. Electromagnetism. Electromagnetism is the study of the interaction between electrically charged particles and the fields they create. The fundamental concept is described by Maxwell's equations, which explain how electric and magnetic fields interact and propagate. Let's break down these ideas with relatable examples. Electric charges and fields. Electric charges can be positive or negative, creating electric fields that exert forces on other charges. For example, rub a balloon against your hair. Electrons transfer from your hair to the balloon, making the balloon negatively charged and your hair positively charged. The balloon's electric field attracts small pieces of paper. Magnetic fields. Magnetic fields are created by moving electric charges or certain materials like magnets, exerting forces on other magnets and magnetic materials. For example, a bar magnet creates a magnetic field. Sprinkle iron fillings near the magnet, they align along the magnetic field lines, showing the field shape. Electromagnetic induction. Electromagnetic induction is the process where a changing magnetic field creates an electric current in a conductor. For example, move a magnet back and forth inside a coil of wire. This induces an electric current in the wire, the principle behind generators. Maxwell's equation simplified. Gauss's law for electricity. Electric charges create electric fields. Example, a charged balloon's electric field attracts small pieces of paper. Gauss's law for magnetism. There are no magnetic monopoles. A magnet always has both a north and south pole. Example, break a magnet in half, each piece will still have two poles. Faraday's law of induction. A changing magnetic field creates an electric field. Example, moving a magnet inside a coil of wire creates an electric current. Ampere's law with Maxwell's addition. Moving electric charges, currents, or changing electric fields create magnetic fields. Example, running electric currents through a coil of wire creates a magnetic field, like in electromagnets. Electromagnetism is all around us and plays a crucial role in many aspects of our daily lives, from powering our homes to enabling communication and entertainment. Understanding these concepts helps us appreciate the technology and phenomena we encounter every day. Relativity. Relativity is a groundbreaking theory developed by Albert Einstein that changed how we understand space, time, and gravity. It has two main parts: special relativity and general relativity. Special relativity. Special relativity deals with objects moving at constant speeds, particularly close to the speed of light. It's based on two main postulates. 1. The principle of relativity. The law of physics are the same for all observers, regardless of their constant speed or direction. 2. The speed of light is constant. The speed of light in a vacuum is always the same, approximately 300,000 kilometers per second, no matter the observer's motion. The key concepts in special relativity are time dilation. Time appears to move slower for objects moving at high speeds compared to those at rest. For example, if you travel on a spaceship at a significant fraction of the speed of light and return to Earth, you would find that less time has passed for you than those who stayed on Earth. This is often illustrated using the twin paradox, where one twin travels at high speed in space and the other remains on Earth. The traveling twin ages slower than the one on Earth. Length contraction. Objects moving at high speeds appear shorter in the direction of motion. For instance, if you observe a spaceship traveling close to the speed of light, it would look shorter along the direction it's moving compared to when it's at rest. Mass-energy equivalence, described by the famous equation E equals mc squared. It states that mass and energy are interchangeable. This means a small amount of mass can be converted into a large amount of energy, which is the principle behind nuclear reactions. General relativity. General relativity extends special relativity to include acceleration and gravity. It explains how massive objects like planets and stars warp space and time, creating what we perceive as gravity. The key concepts in general relativity are curved spacetime. Mass and energy can curve spacetime. Imagine spacetime as a stretched rubber sheet. Placing a heavy ball, like the sun, on the sheet causes it to curve. Planets aren't really pulled by gravity, they're just moving along these curves, like marbles rolling around a dip made by the ball. Gravitational time dilation. Time runs slower in stronger gravitational fields. For example, a clock closer to a massive object, like on the surface of Earth, will tick slower compared to a clock further away, like on a satellite in space. Gravitational waves. Imagine throwing a pebble in a pond. The ripples that spread out are like gravitational waves. These are ripples in spacetime caused by energetic events in space, such as two black holes colliding. GPS systems. The Global Positioning System, GPS, relies on both special and general relativity. Satellites orbiting Earth experience less gravitational pull and move faster than objects on the surface. Without accounting for time dilation and the effects of gravity, the positioning information would be inaccurate. Quantum mechanics. Quantum mechanics is the study of very small particles like electrons and photons, which behave in surprising ways. Let's break down some of the key ideas with examples that are easy to understand. Max Planck's discovery. Energy comes in tiny packets called quanta. This means energy is not continuous but exists in specific amounts. For example, imagine you have a light bulb that you can dim or brighten. As you adjust the knob, the light changes intensity smoothly, which might suggest that the energy is changing continuously. However, at the microscopic level, Planck discovered that the light is actually made up of tiny, discrete packets of energy called photons. So, when you're dimming the light, you're not smoothly decreasing the energy, you're actually decreasing the number of photons emitted per second. Each photon still carries the same quantum of energy, but fewer of them are being produced and released. Albert Einstein's contribution. Particles like electrons and photons can act both like particles, small discrete objects, and waves, spreading out and creating patterns. For example, imagine light as both marbles, particles, and water waves. Sometimes, light acts like marbles hitting specific spots, and other times like waves, creating patterns. Heisenberg's uncertainty principle. You can't know both the exact position and the exact speed of a particle at the same time. The more you know one, the less you know the other. For example, think about trying to photograph a fast-moving car. If the picture is clear, you see its position, but not its speed. If it's blurry, you know it's fast, but not exactly where it is. Schrödinger's contribution. Particles can exist in multiple states at once until we measure them. This is called superposition, and it's described by a wave function showing probabilities. For example, think of a spinning coin in the air. It's not just heads or tails, but both until it lands. Similarly, an electron in an atom can be in many places at once until we check. Quantum entanglement. Quantum entanglement is a phenomenon in quantum mechanics. Entangled particles are connected in such a way that the state of one affects the state of the other, no matter how far apart they are. For example, imagine having two magical dice. If you roll one and get a 6, the other, no matter where it is, also shows a 6 instantly. Quantum mechanics shows us that the very small world behaves differently from what we see every day. Particles can be waves, exist in many states at once, and we can't know their exact position and speed simultaneously. This fascinating field uncovers the strange rules that shape our universe. Let's face it, most people forget much of the physics they learn in school. While it's impossible to cover all of the physics in less than 30 minutes, this video shares one stickman's take on what he thinks are the most important concepts in physics to remember. What aspects of physics fascinate you the most? Leave a comment below and let's discuss.